Okay, so good afternoon, good morning. Welcome to IAU Commission G5 series of talks. Our speaker today is Dr. Paul Barklem from Uppsala University in Sweden. Paul did his PhD at the University of Queensland in Australia. Then he moved to Sweden as a postdoctoral fellow, and he now is a professor of astrophysics at Uppsala. Throughout his career, Paul has made several important contributions for the calculation of spectral line broadening and methods to model inelastic collisions with hydrogen. And his work have led, for example, to much more accurate non-LTE abundance calculations for solar-type stars. His talk today will be on inelastic collisions, hydrogen collisions in stellar atmospheres. And before we start, we would like to ask if you could please mute yourself and switch off your cameras. Questions will be mostly at the end, but Paul is also happy for you to ask a clarifying question during the talk if you wish, by either putting your question in the chat box or raising your hand to ask it directly. Take it away, Paul. Thank you very much.
Okay, thank you, Katja, and thank you all for the invitation, and thanks for coming to listen to the talk today. So as Katja said, I'm going to talk about work that has been done on inelastic hydrogen collisions in stellar atmospheres, and in particular, so I'm going to talk in the first half of the talk about the theoretical calculations, but then in the second half of the talk, I want to focus on the experiments that have been done in the last, I would say, less than 5 years on this topic, and which I think are giving us a lot of guidance on where to go, and will give us even more in the future. There have been many collaborators over the roughly 20 years that I've been working on this problem, both in terms of the atomic physics and the application to non-LTE calculations and modeling. And so this is a non-exhaustive list of people who have been involved. I'll just mention especially the people working with me now at Uppsala University, Anisha Masi and Jon Grummer, and then all the people at the Desiree experiment in Stockholm who are very important in the experimental results that I'm going to show towards the end of the talk. So I understand that this audience is mostly people who understand stellar spectra and maybe non-LTE modeling, but a very quick introduction to where what I'm talking about fits into the overall picture. So we want to be able to model stellar spectra as accurately as possible to then interpret the observed spectra in terms of composition, effective temperature, log G, and other things we can get out of that, like ages and so on. To do that, we need atmospheric models, the macrophysics of the stellar atmosphere, convection, the radiative transfer through the medium. But then also we need the corresponding microphysics. And if we're doing that in non-LTE, then we need to understand all the collision processes, the radiative and collisional processes that go onto the atom that is producing the spectral line. So for example, if we would have a sodium atom here in the middle, then it's surrounded by, in a solar type star, it's surrounded by lots and lots of neutral hydrogen. So these are the green particles, but they're moving very slow. And then they're just, you maybe can't see it so well in here, but there are just 1 or 2 electrons and they are moving very fast. And then the point is that we have understood for a long time that because the electrons move fast, that both means that the collision rate is higher than for hydrogen. So the collision rate per particle, but also electrons are more effective at creating inelastic processes. But then the question has been for many years, if the abundance of hydrogen, which is many orders of magnitude larger than electrons, overcomes this difference in efficiency, because the slow hydrogen collisions first means that the collisions don't happen as often per particle, and then they're very inefficient because the collision happens slow. So from an atomic point of view, this means that the atom can adjust as the hydrogen atom goes past, and inelastic processes are rather expected to be not very likely. So this was a question that already came up in the 1950s, and then in the 80s in particular, people started thinking about this in detail in non-LTE calculations. And but the problem has been that there's been practically no data, at least at that time, there was no data for these kinds of processes with hydrogen atoms. So just an example of why this is important. So I'm going to use the solar oxygen abundance as a interesting case here, because it's very important. Oxygen, the third most abundant element in the sun. We're forced to measure it essentially mostly from the triplet, which has no well-known departures from non-LTE. And at present, the abundance of oxygen in the sun is under debate, and whether it's a high or a low value. And you can see here some example values for using 3D non-LTE calculations, and still in these calculations, one of the main uncertainties is the hydrogen collisions. But progress is being made. So 10 or so years ago, people were forced to use things like the Darwin formula, which I'm not really going to talk about, but a classical estimate. Now we typically have, since 2018 at least, we have some quantum mechanical calculations. But as I'll show, there's still some uncertainty in these. Just to show you on the right here, this is the electron collisions for oxygen are, I would say, well known at the moment. So this is a comparison of calculation by Tail and Zazzarini, and my own calculation, and with two slightly different methods. I know it says they're both R matrix methods, but they use different underlying methods for the atomic structure. And so the outer lines are an order of magnitude, and the inner lines are a factor of 2. So we can see for most transitions, they agree within a factor of 2. The most important transitions are in circles. And so this is very good agreement for the electron collisions. So the initial calculations that were done in say the 90s, and there was one experiment done on the excitation of sodium by hydrogen. They both indicated that the main mechanism for hydrogen inelastic processes would be the so-called voided ionic crossings. So what happens in the atom when the two atoms come together is that at some point, so if we think about say a lithium 3s atom and a hydrogen 1s atom, so hydrogen in the ground state coming together, so this is internuclear distance, at some point they will come together and they will reach an energy which is the same as if they would, rather being two neutral atoms, we would have lithium plus and H minus. And then we get this so-called avoided crossing in the potentials, which means that at this point, a non-adiabatic or inelastic process can happen. And typically that will be that it goes into a state which looks more like lithium plus H minus in that case. And then what this means is actually it's more likely actually that a process like charge transfer will happen rather than excitation. So for this to lead to excitation, you need this to happen twice. You need to pass through 2 avoided crossings, whereas if you pass for charge transfer, you only have to pass through 1 avoided crossing and have a transition happen. So you would come in, say, along this path, the 2 particles getting closer together, and then at this point it would jump up onto this sort of ionic curve, and it would leave as a positive ion and a negative ion. So in this case, lithium plus and H minus. So this we would call ion pair production, and the reverse process we would call mutual neutralization. which is I've highlighted here because I'm going to talk about that, because that's one of the things we can probe with experiments is the mutual neutralization. So that's the reverse process where you would go from a positive ion, and a negative ion going into two neutral particles. So here we see it schematically. They come in, they form a molecule, and then they leave as two neutrals. Then these processes were shown to be important in non-LTE modeling for lithium, sodium, and magnesium in these references. So this is a movie that tries to show what's actually happening. So it approaches along as, so if I go back now, so you start with a lithium plus ion in the middle, H minus ion coming in for this mutual neutralization process. So we're up here, the population is all in this state, and it's going to come in, and at the crossings, there's going to be some change of population. And this is not actually a real calculation. This is where a calculation that just shows what happens. So I've made the probabilities larger than they really are. So, but you can see what happens is that when you get to the crossing, then you see some change in the electron cloud distribution. And as you pass through each crossing, then the sort of probability splits. So that this is just a sort of one way to think about it. So of how you can possibly get from lithium plus H minus into a given state of lithium and hydrogen. And of course, the reverse process happens as well. Okay, so how do we calculate this now? So this is considered to be the main mechanism for this process to happen. There's several different ways that we can calculate it. And at the start, we predominantly, and the people working on this did quantum chemistry calculations for the molecular structure and full quantum scattering calculations for the collision dynamics. And this is what we would call a full quantum calculation, but these are very intensive. They take a lot of time, a lot of computing power, or reasonable amount of computing power. They're very difficult to get to converge, and so this typically takes quite some time. So after we did some calculations with the full quantum method, which I'll come to in a minute, for simpler systems, we've predominantly been looking for ways to model more simply the basic physics to get quicker, calculate first of all to do the calculations quicker, and then second to also be able to do them for very complex atoms like say iron or oxygen, which we want to do. And so then there's sort of more, the two main approaches that have used the one by Belyaev and collaborators is the semi-empirical way of estimating the couplings, and then using the Landau-Zener model to do dynamics. And then my method is the so-called linear combination of atomic orbitals method for the couplings, and again, Landau-Zener model for the dynamics. There's also a third method, which I've investigated recently, called the Landau-Herring method, which is not as good as the other two, but is interesting for some other reasons. Okay, so this is the this progress on the calculations is that we started with the full quantum systems. The first one was lithium, produced in 2003, roughly. So that was together with Andrei Belyaev. And then we worked on sodium for many years, and then magnesium a little bit. But then really when we got the model approaches where we started to understand what was going on, we could increase the rate of calculations. And so over the last decade or so, there's been roughly two systems calculated per year, I would say, a lot due to Andrei's work on this. And including complex atoms like iron and oxygen are in there in 2018, and we see manganese and copper has been done recently, nickel, strontium. So these have been estimated. And then as well, some of the very important systems have been attacked more than one time. So oxygen, for example, has been, there are 3 main papers out there. So I did it with the LCAO method. It was done by Belyaev and collaborators using quantum chemistry plus the probability current method. So that was the sort of in between method that I made for the dynamics here. And then also quantum chemistry plus Landau-Zener in 2019. Okay, so this shows another way to progress in the calculation. So rather than with time, this shows across the periodic table. I hopefully haven't missed any, but I think I've got most of them. So as you can see, all of these simple alkalis and alkaline earths have been done. We're getting there with the open shell elements over here, which are very astrophysically important. And again, the iron group is slowly being filled in as well with data using this these model approaches. So here is an example for what the data sort of looks like, what processes it says are important. So this is so first of all, if we look on the right side, this is a grid showing the states, and then the important thing to notice is that these last states on the grid are the so-called ionic states, where oxygen is an ion and hydrogen is a negative ion, and up here the same. So this process here is the so this is the initial state. So this is the mutual neutralization, and darker means more probable. So we see that these processes are very likely, the charge transfer processes, mutual neutralization, ion pair production. And then we also get these transitions between intermediate excited states. And so what this does to the oxygen atom is it predominantly couples these higher lying states, or the states which are roughly 1 electron volt below the ionization energy, to the continuum. And then there's also coupling predominantly between states which are very similar, but just differ in spin. So they're very close in energy. So it's very easy to go from, say, 4s quintet to 4s triplet system. So that was the main results. And then this has been applied by Anish Amarsi in oxygen to non-LTE calculations. Then we have a small issue of what to do about the Rydberg state, or the more excited states. So this mechanism doesn't work for states which are very excited. So I have another, there's another method that was developed by Kalakis in the 1980s, and I've written a code which does that, which is freely available on GitHub. And so these are used for the Rydberg states, but then you have to figure out a way how to mesh these two sets of data together. And so Anish found, actually, if you're looking at the position on the solar disk here, so the mu angle, the abundance that's measured in 3D non-LTE, we see if we just use the LCAO data, then we have a slight slope. But if we add in this impulse approximation data and keep it even for the cases where we have LCAO data, then things get better. So this impulse S is a quick way to calculate the impulse approximation, and the black impulse is a more detailed calculation. And you can see then that the abundance is roughly flat with disk position. So this seems to indicate that that the LCAO plus impulse used everywhere is better, assuming everything else is correct, which of course is an assumption. But it's not, from a physical point of view, unexpected that there might be another mechanism involved in these collisions. Okay, and just to show that this matches the line profiles rather well. So these are the line profiles at different mu angles and the model calculations. But the problem with this is that the impulse approximation, while it's physically motivated in terms of that, we can understand from a physical point of view, there might be other mechanisms than the ionic crossing mechanism. The way we calculate it is not expected to be good except for Rydberg states. So this is maybe not the best. We don't expect the impulse approximation necessarily to give good results for low-lying states which are involved here. Okay, So then I wanted, as I said in the introduction, I wanted to talk about the experiments, because I think this is where things have been really moving forward in the last 5 years. So-called merged beams experiments. So there are 2 places where this is being done, at the university, the Catholic University in Leuven in Belgium, and Stockholm University in Sweden, which luckily happens to be just down the road from where I am. So the basic idea with the merged beams experiment is that take a beam, say, of lithium plus here, you take a beam of deuterium minus. So often in these experiments, the deuterium is used instead of hydrogen for reasons of that you want the mass difference between the 2 particles to be as low as possible. But deuterium is expected to act in pretty much the same way. There are experiments now with hydrogen. I'll come to that. But at least at the start, people were using deuterium for the most part because it's easier in the lab. Then the point is they go into an interaction region where the 2 beams are going along together, and that leads to a very small relative speed. So this is, you want to get down to low energies. So the typical collision energies that are in a stellar atmosphere, for example, are less than an electron volt. So you want to get into the kind of milli-electron volt regime in the relative velocity between the 2 particles. And so the way you do that is you have 2 beams of fast particles which are then moving very slowly relative to each other. And what happens if they react with each other in here, then they gain energy because, well, if we go back to our diagram of the potentials, there's a lower energy going into the neutral states. And so they get a kick, and the 2 neutral particles fly off, and some of that will be in the transverse direction, and the particles will have a distance from each other when they hit a detector later. And so the point is the distance between the particles tells how much energy was released, and then thus how much, which states were populated. So this is the Desiree experiment in Stockholm. So this is actually a double ring. So it's and this is the merging region we talk about. So you can keep the particles in these rings, and if you want, or you can take them in with a single pass, and then when they interact in this region, then they come straight out this end section. So these are the experiments that have been done. So I've kept the green for where we have theoretical calculations, and then the blue now is where we have experiments. And for the most part, the experiments have been repeated in many cases, both in Leuven and in Stockholm, which is an important check, of course. So lithium and magnesium have been done and published and analyzed, and there are also experiments for carbon, nitrogen, and oxygen, which are at present unpublished and for the most part not totally analyzed yet. And as I said, some of the experiments are with H-, some with deuterium minus, for practical reasons. As I said, you want to keep the difference between the masses as low as possible in many cases, or at least within a range that can be handled by the experiment. But now many of the experiments are using hydrogen. So the simple system, so if we start with these, with lithium and sodium, so this is, they seem to follow what we would naively expect. So this is showing the branching ratios, so into the 3s state of lithium. So hydrogen goes into, lithium, so it will actually be deuterium, not hydrogen. Hydrogen goes into the 1s state, lithium plus goes into the lithium 3s state. And this is the main channel. More than 60% goes in, or roughly 60% according to experiment. And we can see that the theoretical calculations, so the first one is the full quantum, is the this sort of reddish line here that gives the best one, although it doesn't go to very low energy. Then if we look at the calculation where it's hydrogen instead of deuterium, then it's a little bit higher and a little bit more off. And then if we use the LCAO theory, then we see that it's a little bit worse, but not hugely worse. We're getting very close with deuterium. This is the line, what it would be hydrogen. And then this is the prediction, my semi-empirical calculations. And then the experiments, so the full ones are from Desiree from Stockholm, and the open ones are from Belgium in Leuven. So they agree very nicely. So we can see roughly what we would expect in terms of the more sophisticated theory agrees with the experiments better, and then the disagreement gets more as the theory gets less sophisticated. But this trend, so that trend continued for sodium, but not for magnesium. So this is work published recently by Jon Grummer as the lead author for magnesium with deuterium. And here, so this is the sort of the results in terms of the experiment. So here we see the distance between the particles, which is reconstructed. And then you can identify the peaks with different states. And then this panel on the right compares with different models. And so if we use the full quantum calculations here, then that's the red line that agrees rather poorly with experiment. Whereas the LCAO calculations, they agree much better. So actually quite well. There may be some differences down here for the state, but for the most part, it gets the main trend correct. And this may be because the full quantum calculations didn't include enough states correctly. So already in magnesium, we see the problems that can be encountered in trying to do sophisticated calculations, it seems. Okay, back to oxygen. Unfortunately, I can't show any results, but because there has been a lot happening on this. There was an experiment carried out on O+ with D- in Leuven, and that was part of a PhD thesis, which was defended last week. And then there was an experiment done at Desiree with H- in Stockholm just 2 weeks ago, led by Alice Schmidt-May. At the moment, the processing and analysis is in progress, and there will need to be comparison with the experimental data and comparison with theory, but we hope that these experiments will tell us something about which calculations among the three at the moment that we have for oxygen best model the ionic crossing mechanism. And so the hope is that this will tell us whether we're modeling at least this ionic crossing mechanism correctly in oxygen, and then we can start thinking about what this other process might be on the basis that we then know that we modeling this process correctly, or it might tell us that we're not modeling this part of the process correctly, and this could explain this need for this these extra collisions which come in through the impulse approximation. Okay, then just to say a little bit about some other systems which are they also teach us about the physics. They're not interesting necessarily for stellar atmospheres, but they could be in principle. They are definitely interesting in the Earth's atmosphere, and in principle could be interesting in other planetary or even exoplanetary atmospheres. And so recent experiments have been done on nitrogen plus with O- and O+ with O-. So these processes are important in the Earth's atmosphere. These experiments have been led by Matthias Paulin at the Desiree experiment in Stockholm. There also were experiments earlier by Direct et al. in Leuven. So, and these calculations tend to show some interesting physics in terms of that we have to include so-called configuration mixing to reproduce the experiments. So in particular, there is this this state, if you take nitrogen plus with O minus going into nitrogen with oxygen, this state here is poorly predicted if you don't include the so-called configuration interaction, configuration mixing. So what that means is that really the state, like its real wave function, is a mixture of two configurations which look like 2s 2p4 and 2s squared 2p3 NL. So this means that the simple ways that we model the wave functions in the normal way we do the calculations break down. But if we include this mixing, then we get almost a perfect agreement here. And you can see that in general, there's reasonable agreement between, at least we get the ordering of the states correct. So the most important state is correctly identified, and the second most important, third most important, fourth most important are all correctly identified according to experiment. Another thing that we see in these experiments with complex atoms is we see evidence of so-called 2-electron processes. So this is where 2 electrons do something when they come in. So what I showed you earlier was the ions come in together and then 1 electron jumps between the atoms. 2-electron process would be, say, 1 electron jumps and another electron changes state or something like that. And these processes we generally expect to be very rare or not very likely, but experiments seem to show that in these complex atoms they're more likely than we think from theory. So my conclusions. So the model approaches that we've used, they seem to provide a very useful way to obtain estimates for astrophysical modeling. So as we saw, there's been a lot of progress. We have data for a lot of systems now, and it's relatively quick to produce them. They seem to agree well with the experiments so far for the simple atoms. So for sodium and lithium, the agreement is very good. And so in terms of astrophysical modeling, that probably means that these model approaches are probably sufficient for these cases. But we see some evidence from oxygen, at least from the center to limb variation in the lines, that at least if we believe the rest of the modeling is correct, then there seems to be some need for some more or more efficient hydrogen collision processes than what comes out of our calculations. The experiments are in the pipeline, and hopefully they will tell us something about this. So these complex systems like nitrogen plus O minus and O plus O minus, they have at least suggested 2 possible things to look at, and that is configuration mixing, so that the wave function is more complicated than we think in our models and our simple models, and multi-electron processes. So especially 2-electron processes. There may even be some hints of 3-electron processes in the data. So my conclusion is there's still work to do on the open shell atoms, and what we learn will likely apply to other complex atoms like the ion group, which are an experimental challenge. So as I mentioned, the reason one uses deuterium often is because one wants the mass difference to be as low as possible in these experiments, but the mass difference is by definition very high when we go to the ion group compared to either deuterium or to hydrogen, and so these are out of reach essentially of the experiments at present. So we hope we'll learn something from up here that will tell us about what maybe is going on down here. Okay, thank you for listening.
Thank you so much, Paul, for a great talk.
Thank you.
So we'll go to questions now, and Guillaume is going to lead the process.
Yeah, so if you have any question, please either ask them in the chat or raise your hand, and then I will ask you to unmute yourself. So is there any question? So Charles, please.
Could you talk a little bit about the possibility of interactions with hydrogen affecting the fine structure levels, and could that be significant for line broadening?
Okay, so you mean inelastic processes between fine structure levels by hydrogen collisions? That's what you...
Correct.
Yeah, so some of the calculations that have been done by Belyaev and other groups, for example, for copper and for calcium, they have done calculations where they take fine structure into account. And there they do find some differences in terms of the population into the different fine structure levels for calcium and copper. So this is something that is another possibility of a thing that we might need to take account for in future calculations. And so the theory is there now to do that, and there are examples of how you do it. Then the second part of your question of how that would feed into line broadening. So that the basic assumption is that for at least for low-lying transitions, that the elastic component dominates the line broadening, and that generally as you go to Rydberg states, then there might be an inelastic component of the line broadening. And so the basic, okay, sort of hand-waving argument would be that the ionic crossing mechanism, at least this will be predominantly affecting the low-lying states, and therefore it shouldn't be very important, but it could be important in the high-lying states. So that would be. It's actually something that me and my former supervisor wrote a paper about in about 2001, is about the possible effects of the ionic crossing mechanism on broadening by hydrogen, but we've never done calculations. In that case, we did simple estimates of what the tunneling time is, and that sort of indicated that the effects would be small.
Thank you.
Have I answered your question? Yep.
Yes, thank you.
Okay, thank you. And also we have a question from Tatiana.
Yes. Do you hear me?
Yes.
Okay, Paul, could you tell us what is the best present oxygen solar abundance?
No, I can't at the moment. So no, I don't have a strong opinion. All I can say is that my name is on this paper. So
this one.
Yes.
Amarsi.
Yes.
Okay. Thank you.
Yep.
So on the chat, we have a question. I think it's related to the previous question from Charles. So the question is from Sandra Weaver, which is there an interaction between this effect and the linear Stark effect?
No, there isn't. So there would be, so the linear Stark effect would occur in hydrogen. And then there can be, so I looked at hydrogen processes. So the process we would be talking about would be H plus, H minus going into hydrogen in the 1s state and hydrogen n equals 3 state. It's essentially it almost all would go into the n equals 3 state. And this process seems to be rather unimportant compared to the, first of all, as you say, the linear Stark broadening. Then you have so-called resonance broadening of the Balmer lines. And then you would have on top of that, so what I was talking about with Charles, you would have a inelastic component due to this of the broadening, which would be then even smaller again. So I would say that linear Stark is number 1, resonance broadening is number 2. Then you probably would have what you would call sort of the normal elastic van der Waals component, and then the inelastic component would be number 4 on my my sort of rough guess, or we've done calculations. So
Thank you.
okay.
Yeah. So Andre, I see that you have a question. So unmute yourself, please, and ask it.
Do you hear me?
Yes.
Yeah.
Yeah. Hi, Paul.
Hi, Andre. How are you?
Nice to see you.
Yeah.
In your recent paper, Physref Letters,
Yes.
you wrote the conclusion that your model approach, so-called linear combination of atomic orbitals, works better than full quantum approach. So this is absolutely against the general opinion.
Yeah, that's what I'm saying. This is against
so that's my
what we
question,
expect.
whether you really believe that your model approach gives more accurate results than quantum.
Well, it's clear. I mean, you see here the full quantum predictions are the red line, and the LCAO is the green and the blue line for hydrogen and deuterium. But I do believe that if you do the full quantum calculations with these higher states included above, so the problem is that these states up here are at the border of the full quantum model. So I think the problem is that you need to include some higher states here for this to be modeled correctly. But so if I think that if you increase the size of the full quantum calculations, they will be better.
Paul, you know that we have done this. You did not cite our paper where we have extended.
I have not seen this.
It's Chemical Physics 2015.
Okay, then
and
I have not.
The editor of that SU.
Okay, then I will have to check this calculation.
Okay, thank you. So Katja, you have a question?
Yeah, Paul, do you mind that I go back to the oxygen abundance in the sun problem?
No.
I see that the calculations from Anish give 8.69 and Maria gives 8.74 for all purposes when you're doing an abundance analysis. This is an excellent agreement. Do you disagree with this statement, or how accurate? I see your uncertainties are 0.03, but all things considered and considering what you talked about today and need to improve things, is there a tension?
I mean, I agree with you that for any other element we would accept probably this, but the problem is the solar modeling problem. So I mean, as I'm sure you know, that this does make a difference because oxygen is so abundant. So that's why we're not happy with this difference, I would say.
Of course, I understand. With helioseismology, you mean, right? The tension with helioseismology, sure.
Yes.
But I'm saying from the point of view of the calculations, can we really say these are different values? And how do you see that the oxygen abundance in the sun will go as you consider more things in your modeling for oxygen?
Oh, I mean, we don't know. I mean, there are different assumptions about the hydrogen collisions, and then there are other differences between the modeling as well. So, and then of course it would be nice if we could get things to match with the other diagnostics, and those agree in some of the studies where it's done. But you have the permitted line, and we have the molecular. But they have complications of blending and molecular lines and so on. So, so for the moment, this is probably the most accurate way to do it, the most reliable.
Okay, thank you.
Thank you. So if there is no any other question, let's thank Paul again for his very nice talk, and thank you all to have come to this seminar.
Okay, so thank you so much. So we'll see you